objectives?
5 minutes.
Only 5 minutes.
Yes.
What happened? It is not 25 minutes.
It is close to 25. Just
Summarize it. Yeah. So this is the slide that shows the innovative that have been adopted by the ANIA so far the production of electricity using CFD technology is concerned. So these are the innovations introduced by ANIA. ANIA introduced new heat carrier molten salt, a mixture of 60% of sodium nitrate and 50% of calcium nitrate in order to increase the operating temperature and possibility of storing heat. Then another innovation of ANIA is the design of a new type of concentrator based on thinner layer that saves construction and installation cost and the use of large-scale heat storage. Another innovation in the architecture product enables the plant to provide heat to the steam generator constant rate of 24 hours a day. Then 5 megawatt passive solar plant costing nearly 60 millions of euros having unique characteristics so to collect and conserve thermal energy of the sun for many years, thus enabling the plant to generate electricity both during off sunshine hours and during the overcast time. So this is a slide that will tell you that why we are using the molten salt instead of the diatomic oil. So I will not go through it. Then this is another new innovation that has been done by ANIA. So ANIA presents the innovative design of world first solar disk consisting of solar mirror capable to focus up to 2000 times the solar radiation on a small focal area. So the novelty of this system consisting of a solar disk power system, the use of air microturbine engine tried for the very first time compared to the Stirling commonly used in the backup application. So the most operational CSP stations are located in Spain, Italy, and the United States. Other countries like Finland, Denmark, Israel, Ukraine, and also make use of such systems for electricity generation. Spain and the United States lead the ranking with the highest installed and operating power using this technology. So the India first 2.5 megawatt CSP plant was commissioned in April 2012 at Bikaner, and the technology used that was from our institution. So this slide is about the photovoltaic. As a brief note regarding how much does it cost to produce 1 kilowatt hour using renewable energy sources, as per information available from the literature, it is to be noted that the hydroelectric power comes in at an average of 0.5 kilowatt per kilowatt hour. Onshore wind, photovoltaic, biomass, and geothermal below 0.10 cents per kilowatt hour, and offshore wind at 0.30 per kilowatt hour. With respect to the cost to generate 1 kilowatt hour of electricity using PD, a kilowatt hour of generation from a 1 kilowatt capacity at a cost about 0.10 per kilowatt hour when the cost is amortized over the life of the system. The cost of kilowatt hour from a much larger area will be much less than will be much less in the range of about 2 cents per kilowatt hour over life of the system. So the primary challenge in the photovoltaic sector focus to increase energy efficiency, making the structure capable and reduce dispersion as much as possible. So this is the two slides for the biomass. So I will not go through all these things. I will just tell you that what we are doing over there. So the gasification is currently considered a more attractive process when compared to the combustion and pyrolysis for both biomass and waste treatment. Moreover, it represents a cleaner alternative solution with respect to reducing environmental restriction. The number of experimental plants based on different technologies, fixed bed, BFD, then passed internally circulated through the bed gasifier or different sizes, ranging from 10 kilowatt to 1 megawatt capacity. They are available at our center, and I am happy to say that our center is the only center at the European level where you can have all these plants. They have been designed, experimented, and they are running in the running condition. So just to say that the fixed bed gasifier plant of power capacity 25 to 30 and 80 kilowatt electric, most appropriate for them used in the agriculture sector, especially in the developing country, have already been designed, developed, and installed at our research center. This is the novelty of the
request, please summarize.
yeah. So this slide will give you that what we have done. So for the biomass gasification concern, I am sorry to say that even as of today, in India we are using air as the gasification agent. So what does it mean? The calorific value of the gas which we are getting, that is very low, and moreover the pollutant gases present in the produced gas, they are very high. Okay. So the second thing, our main aim was to increase the percentage of hydrogen in the produced gas. So what we did at our center to obtain a syngas with heating value comparable to that of the syngas from CFBR, a mix of steam and oxygen was proposed as a gasifying agent, thus avoiding the dilution of the syngas by the inert nitrogen of the air. The use of steam as gasifier agent gives help to obtain almost pollutant-free nitrogen, free hydrogen, enriched product gas with a high value of 12 megajoules per normal cubic meter of the dry gas compared to 4.5 megajoule. Then the purification of the product gas is obtained thanks to the inclusion of high temperature ceramic filter in the cleaning section. Then moreover an adequate purification of the product gas is obtained thanks to the inclusion of a high temperature ceramic filter in the cleaning section. By adding in the reactor specific catalyst, the hydrogen content in the produced gas can go up over 64% and its quality can be further improved. So this slide will show you the all these different plants. These are in the capacity of 10 kilowatt to 1 megawatt thermal capacity. These plants have been installed and experimented and the results are shown in the slide. I will not go for a second generation biofuel. This is from the immunocellulosic biomass. These are our conclusions. And then I would like to convey my thanks to the triple ITM, Gwalior, especially to Professor SM Singh and Dr. Anurag Srivastava. And of course, my thanks are due to my official from India, Engineer Giorgio Grandicchi, Director General, and then Julia Monteleo, Director Department of Energy Technology and Renewable Resources. And last but not the least, the text used in the presentation from various software worldwide is duly acknowledged as well. And thanks to all for your valuable time and patience. Thank you very much.
It is very difficult to accommodate any organization and development in such a short time. So even then, thanks, Dr.
This one session, so that is it.
Yeah, because just to cover all these things, just 20 minutes, not possible.
I request respected chairperson sir to present the moment.
One more thing that I would like to share with the young student is that if somebody is interested to apply for PDF, then there is one site that is ICTP, International Center for Theoretical Physics, ictp.it. And when you will go to that site, search for Training and Research in Italian Laboratories, that is called TRAIL program, Training and Research in Italian Laboratory. There you will find all the information, how to submit your application and where to apply and when to apply. Okay.
Okay. Okay, so we have two more presentations from the young scientists, and this rest part will be taken care of by Dr. Suman, who is professor in Kurukshetra University. So please, Suman.
Thank you, Dr. Hashmi. And for the first short invited talk, I'm inviting Dr. Harshita K. Patil from MGM University, Chhatrapati Aurangabad. So you have 10 minutes for.
A very good afternoon to everyone. Myself Harshita Patil. I work at MGM University, Chhatrapati Sambhajinagar, Maharashtra. Today I am presenting a research paper entitled Voltammetric Sensor for Sensitive Detection of Mercury Ions using polyphore methyloxylene SWT's composite. This work I have done with my professor. So basically, this paper aims to synthesize polyphore methyloxylene, which is called as P4Mnether. The composite is made with SWT's composite. After finalizing the synthesis parts, we have utilized this nano composite for voltammetric detection of mercury ions. So, the detection of these mercury ions is done utilizing a voltammetric. By utilizing the electrochemical setup, we have performed the detection. The results were outstanding because this particular sensing element has achieved a maximum contamination level detection. So this 4 microgram per liter detection level was optimized and not optimized, it is performed. So this is a graphical abstract. First of all, we have utilized a platinum as a working electrode, which is on which the composite was synthesized on the platinum electrode. Then, then we have exploded for the then it is explored for electrochemical detection. So we all know the entire world is facing a problem, which is definitely a global warming. Global warming is caused due to pollution. Now there are different pollutions. So out of that we have targeted water pollution. Now why water pollution happens? So there are so many reasons. The anthropogenic activities performed by us only. So there are, again, when we talk about water pollution, so there are many types of water polluted. Out of that, we have targeted heavy metal ions. Now when we talk about heavy metal ions, so there are so many heavy metal ions. So basically when we talk about nickel, iron, cobalt, iron like substances, heavy metal ions, so they are basically needed. But once they exceed the level, what we are going to face, we are going to face the adverse effect of the same. So that is why now again now here we have targeted in this particular paper we have targeted a mercury ion which is a carcinogenic. So that is the need of the hour to think about detection, quantification, and qualitative analysis has to be done. If we have a particular water sample, so what exactly the ions it is going to have, and if the concentration is going to exceed, we need to take an call. We must know what is the concentration of particular ion. So our approach. So electrochemical sensor we have thought about. So why electrochemical technique only? So there are so many techniques to detect the heavy metal ions. But when we discuss, when we think about this approach, so electrochemical sensors are very simple. We can utilize a portable device. The work we have performed that is at laboratory scale, but we can think of a electrochemical setup which can be portable. So the advantages of utilizing electrochemical sensor is simple instrumentation. Sensing can be controlled through optical wires, and so this is very easy. We can opt a portability. So again, it has very good sensation. So when we talk about an ideal sensor, so sensitivity is one of the factor which we have to talk about. So in this paper, we have utilized a platinum as working electrode, AgAgCl as a reference electrode, and the electrode which is counter electrode, that is again a platinum. So targeted materials were definitely the P4MA and single walled carbon nanotubes. So first of all, why carbon nanotubes? So carbon nanotubes are going to have very unique electrical properties. It is efficient to work in heat also. Again, since it is a nanomaterial, has high surface to volume ratio, extraordinary in strength and sensitivity. But again, its disadvantages are slow charge transduction and decrease in band gap after high doping. Sorry. So these are the limitations of carbon nanotubes. It is hydrophobic in nature since we are targeting the material to explode for the water detection. But carbon nanotubes are hydrophobic, and so forth we have explored organic conducting polymers, say P4MA. So that is the point why we have targeted a nanocomposite. It has polycomb structure. Due to this structure, whatever analytes comes, it is going to be detected by this. So again, a selectivity issue can be addressed when only carbon nanotubes are explored. After that, the pH of analyte affects on the surface of the CNTs. Less reproducibility and lifetime in harsh environment, dislodging from the surfaces. So these points have to be addressed when we talk about a sensor, but this we can address by utilizing the organic OCPs, the organic conducting polymers. So we have utilized the organic conducting polymers, which are environmental stable. They are stable. They can be worked in normal room temperature. Ease of synthesis we have, sensitive for low level perturbations, electrochemically active. Now, a few limitations of the OCPs: low charge transduction and decrease in band gap after higher doping. Now, these were the advantages and disadvantages of both OCPs and CNTs. Now, our approach. Now, in our approach, what we have done, we have utilized the SWNTs, onto which we had a deposition of OCPs, that is P4MA. So due to that, what happened, since we are utilizing this approach, so it will give surface activity of SWNTs retained, and it will act as a sensing backbone. And latter, it can be utilized for the detection of water pollutants. So our targeted thrust areas were sensitivity, selectivity, and lower detection limit. So this is a synthesis diagram. Yeah, with synthesis diagram where the red colored part is for a nanocomposite, which shows a increase in conductivity, electrochemical activities. The redox curves, these. Okay. So this black colored graph is for synthesis of the nanocomposite, which what we can discuss over here is that we are getting. Okay. Okay. So this is the synthesis graph where we can confirm a more electroactive nature of the composite. Now this is the AFM graph where AFM images where we have addressed the topography, and from images the line profile was drawn, and it shows the good roughness. When we talk about a electrochemically active surface, the roughness plays very good it plays great amount of work. So again, the characterizations were done utilizing CV, acyclic voltammetry, where we can confirm the more electroactive nature of nanocomposite. Again, the AC impedance spectra, where again good electroactive nature of composite is addressed. Now this is FTIR to confirm the confirmation of nanocomposite. Now this is a graph of analytical study. First of all, we have explored P4MA to the mercury ions, where it has shown less sensitivity. But once we have explored the nanocomposite, it has shown good sensitivity. And later, this P4MA SWNT's nanocomposite was explored for different concentration of mercury ions. The detection, the different concentrations are were in this range. Now, this is a linearity curve. It has shown good results. Now, this is a selectivity graph when the nanocomposite was explored for the different cross analytes, so it has shown great amount of selectivity. So in conclusion, the SWNTs have played good role in order to show the good electroactive nature of the P4MA, and the sensor has shown good concentration. I mean, a maximum contamination level was achieved, which is 4 microgram per liter. So thank you.
Thank you, Dr. Patil. Audience has any questions you can ask? One or two questions, please.
Uh, How are you confirming that it will respond to only this Ag plus 2 or any other heavy elements it can also respond to?
So the cross analytical study was done. So this is a graph where we have explored different ions. So this is the graph which is done for cross analytical study. These many were the ions which were utilized to confirm that it is selective toward mercury ions.
And these are the various 9 oxidation and reduction states of the metal after addition of metal and electrons are generated for quinones. First, this MSP calculation shows that the charge present on the sp2 hybridized oxygen here for benzoquinone state, benzoquinone radical anion, benzoquinone dianions, and here the charge goes on increasing from benzoquinone to benzoquinone radical and benzoquinone radical quinone dianions on the oxygen, and all these values are in the kilocalorie per mole. This state shows highest binding energy, negative binding energy. These calculated values for various lithium, sodium, and potassium cations are as shown in the table, and the different oxidation and reduction states of the quinones shows different values of binding energy. But quinone with monocation QM plus state shows positive value of binding energy, and all other state shows the all these values for in front of the oxygen, and R represents the binding energy over the ring of the quinones. Then quinone dianion state also shows highly negative values of binding energy other than all states. For a particular state, if we consider any particular state of the quinone, then binding energy with the cations goes on increasing in the direction of hydrogen to potassium, potassium to sodium, sodium to lithium, and then lithium to hydrogen. In this direction, potassium to sodium, sodium to lithium, and lithium to hydrogen, this binding energy with these cations goes on increasing. But if we see the binding energy change after addition of metal, cation, and electron, means after addition of a metal, these values for various benzoquinone state. Here quinone metal cations state, quinone radical anion state, quinone radical all shows negative values of binding energy, and for a particular state of quinone, binding energy order goes on changing, lithium to potassium, potassium to sodium. Same trend is as shown in the here figure. Is if we add in this direction for various oxidation state of the quinones, here addition of electron and addition of metal, and if we see along this line, addition of metal, binding energy change shows as shown in the figure, and these binding energy values goes on changing for various states, and there. But why these binding energies goes on changing in front of the oxygen, which is a verified with a calculation of rho BCP for various state of benzoquinone lithium complexes. Figures are shown here, and here if we consider for lithium, quinone binds with lithium cations, quinone state with lithium radical, quinone state with lithium anions. These rho BCP values for this particular bond with oxygen atom and lithium, the rho values goes on increasing, and here for lithium dication, lithium cation radical, and lithium dimetal, these values are also goes on increasing direction. These are for lithium. Same trend is observed for sodium and potassium, which are as shown in the table. Here, all the value of rho BCP shows higher the strength of bond due to, if we see the trend, potassium to sodium, sodium to lithium, lithium to hydrogen, these values are goes on increasing and strength of bond increases. Rho BCP values increases in the order of this potassium to sodium, lithium to hydrogen, and these negative values of del square rho with hydrogen cation ion shows covalent bond. It's after binding of a hydrogen with the oxygen, then these del square rho values are reported as a negative, which shows covalent bonding, and positive values of the lithium cation, sodium cation, and potassium cation shows del square rho values are positive, and which represents either ionic or electrostatic bonding is there with oxygen. Same values are reported here in this various state of the quinones for lithium cation binding and rho BCP change. For these values are for lithium only. But if we calculate the ionization, adiabatic ionization potential values and adiabatic electron affinity values for various state of the benzoquinones, here the all higher positive values of ionization potential shows removal of electron is difficult. Means higher positive values of this API, here it shows electron in these various states of the oxidation quinone states, removal of electron is difficult, but negative values of the adiabatic ionization potential shows removal of electron is easy for quinone metal radical cations. And if we compare the adiabatic electron affinity values, high negative values of electron affinity shows addition of electron is difficult, and high positive values of electron affinity shows addition of electron is easy. In comparison with previous binding energy calculation and rho BCP and del square rho BCP calculation, these values are quite different. That is, quinone state with sodium ions binding energy, if we compare with hydrogen ion, lithium ion, potassium ion and sodium ion, which shows electron removal, easy electron removal as compared to this binding energy. Sodium shows from sodium complex we can remove electron more easily, and also we can add electron within that complex more easily. And but trend observed here is slightly different. If we see the trend, previous trend and this trend, these adiabatic ionization potential values, trend is slightly different. Sodium is higher than potassium, potassium is higher than lithium and hydrogen. And from this, we conclude that we have explored lithium ion, sodium ion and potassium ions as well as metal ions boosting ability with a quinone as compared with a H plus ion. Then quinones and its reduced state shows different binding characteristic towards first group of elements, hydrogen, lithium, sodium and potassium. But as decreasing interaction energy with these various complexes, with lithium complex, benzoquinone state with lithium complex, benzoquinone state with sodium complex is better as compared with benzoquinone state with potassium complex, implies that size of ion increases, capacity of quinone to hold the ion decreases. But ionization potential values and electron affinity values of quinone state with sodium ion shows that quinone electron seems to be suitable for sodium ion batteries. And study provides basic insight of the reversible binding of ions to quinone molecules, and this will help in designing electrode material in a rechargeable ion batteries. I strongly acknowledge here Dr. Subhash Pillai sir. He has helped me during my research. Then head department of chemistry, principal of my college Dr. Prakash Patil sir, my research colleague Miss Anuja Ware, Miss Surya, and thanks organizer for giving me chance to present my research work here. Thank you.
Thank you, sir, for such a knowledgeable session. And now it's time for lunch. So I request everybody to have their lunch, and the session will restart at 2:50. Sharp at 2:50. Thank you, sir.
Sir, I want one photo with me. You and this. Sir, I'm Thank you.